The same Qwen model jumped from 60 to 167 tokens per second on the same graphics card, almost 3 times faster, with just one setting. The GPU did not change. The quantization did not change. Qwen simply started predicting more than one token at a time. The feature is called multi-token prediction, or MTP, and Qwen 3.8 27B was trained with it. But here is what makes this interesting. Not everyone gets the same speed up. Some users gain around 30%. In the right coding and agent workloads, the model can get close to 3 times faster, and on the wrong setup, enabling MTP can actually slow it down. Same model, same GPU, 3 completely different results. So where does that extra speed come from, and how can you tell which result your computer will get? In this video, we'll see how MTP works, how much speed you can realistically gain, how to enable it, and how to know whether your hardware can actually benefit. Because MTP can be a major upgrade, but only when the workload and the memory are right. The largest gain appeared during an agent-style task filled with code, JSON, tool calls, and repeated formatting. Those outputs are unusually friendly to MTP. Once the model begins a familiar function call or a block of structured code, the next few tokens become easier to anticipate. Normal conversation gives MTP less to work with. The next words are harder to guess, so more of its predictions are rejected. MTP does not care how difficult your task is, it cares how predictable the next few tokens are. And to understand why that matters, we need to look at how Qwen normally generates an answer. Normally, Qwen produces one token, reads through the model again, and then produces the next. For a dense 27 billion parameter model, moving all those weights through memory for every token is expensive. The GPU can perform the calculations quickly, but it keeps waiting for the same model data to move through memory. MTP tries to reduce that waste. A prediction head inside Qwen guesses several tokens ahead. The full model checks those predictions together and accepts the ones that are correct. If the prediction is good, Qwen can produce several tokens with close to the work normally required for one. If it predicts badly, the speed advantage begins to disappear. The full model still checks every proposed token before accepting it. MTP is designed to change the speed, not the intelligence of the model. Qwen's official model card confirms that Qwen 3.8 27B was trained with multiple MTP steps. That means compatible model files can use MTP on their own without loading a second model. But the model file, quantization, and runtime all need to support the same feature. Having MTP in the original model does not guarantee that every local download is using it. Imagine Qwen is generating JSON. Once it begins an object, the next tokens often follow a familiar pattern, quotation marks, a key, a colon, a value, and a comma. Code works in a similar way. Brackets close. Functions follow familiar structures. Tool calls repeat the same formats. Refactoring can include large sections of code that already exist in the context. This gives the MTP head a much better chance of guessing several tokens correctly. Normal conversation is less predictable. Creative writing is even harder. There may be many equally reasonable ways to continue a sentence, so more predictions are rejected. That is why MTP can approach twice the speed on coding or structured output while giving a much smaller improvement in normal chat. The realistic results also support this. On a single RTX 3090, one controlled community test increased from around 31 to 41 tokens per second. A laptop RTX 5090 increased from roughly 37 to 51. That is an improvement of approximately 1/3 without changing the model or the graphics card. Some coding workloads can gain much more. Normal conversation may improve by only 20 or 30%. And the famous 3 times result belongs near the top end, where the output is especially easy to predict. This does not make the smaller gains disappointing. In a long coding agent session, hundreds of tool calls and code generations can turn a 30% improvement into a meaningful amount of time. If you are already running Qwen 3.8 27B, tell me in the comments what speed you see with and without MTP. Include your hardware, quantization, and context size, because all 3 can completely change the result. But before we turn it on, there is a more important number than tokens per second. That number is your available memory. MTP may already be included in a compatible model file, but running its prediction head still requires additional working memory. Depending on the runtime and configuration, that can mean a few extra gigabytes. If Qwen fits comfortably inside your GPU, this may not be a problem. But if the model already uses nearly all of your VRAM, enabling MTP can push part of the workload into system RAM. And system RAM is much slower than VRAM. One RTX 3090 Ti user saw around 85 tokens per second, while the model remained completely on the GPU. Increasing the MTP setting pushed part of the workload into system memory, and the speed fell to about 58. The speed setting made the model roughly 1/3 slower. This is the part the headline usually leaves out. The catch is that MTP uses additional GPU memory. On a 24GB GPU, a 4-bit Qwen model may leave enough room for MTP and a useful context, but the exact limit depends on the quantization, KV cache, and context length. On a 12 or 16GB card, the trade-off becomes much harder. You may need a smaller context or more aggressive quantization. If any important part of the model moves to the CPU, leaving MTP disabled can be faster. Mac users face the same basic choice. Unified memory can provide a larger shared pool, but every gigabyte used by MTP is a gigabyte that cannot be used for more context. Before changing any MTP setting, check whether Qwen still fits completely in fast memory. That matters more than finding the perfect draft depth. I will use llama.cpp here because it gives direct control over the MTP settings. Llama, VLLM, and SGLang can also support MTP, but their setup is different. In the current llama.cpp documentation, the main setting is spec type draft, MTP. The basic starting configuration adds 2 more flags, spec draft, nmax2, and parallel 1. The first line activates Qwen's MTP prediction head. The second tells it to draft up to 2 tokens ahead. And the final line matches the current single slot setup used by this MTP path. Some older guides use a different name for the MTP type. If you copied an old command, check it against the current llama.cpp documentation. You also need a compatible quantization that retains the MTP heads. Some downloads label this clearly, while others may not include them. Once the model is running, do not immediately increase the draft length. Test a real task first. It sounds logical that predicting 8 tokens should be faster than predicting 2, but MTP does not work that way. Drafting further ahead gives Qwen the chance to accept more tokens in one pass. It also makes the prediction more likely to fail. At first, increasing the draft length can raise speed. After a certain point, Qwen rejects too many guesses and performance begins to fall. The best value changes with the hardware and the type of output. A code-heavy task may benefit from 3 or 5. General chat may perform best at 2. That is why 2 is the safest starting point. Use the same real task several times with MTP disabled and enabled. Compare total completion time, not only the highest token per second number you see. Keep your normal sampling settings during the first comparison. Higher temperature generally makes the next token harder to predict, but lowering it also changes the style of Qwen's answer. That is not a free speed adjustment. Only test a higher draft depth after confirming that the model remains fully inside VRAM and MTP is already helping your workload. If Qwen fits comfortably in your GPU or unified memory, and you mainly use it for coding, tool calls, JSON, or refactoring, MTP is worth enabling. Start with a draft depth of 2 and test a task you actually perform. If the entire model stays in fast memory, you can experiment with a higher value. If Qwen barely fits before MTP is enabled, leave it off or reduce the context first. Losing GPU offload will cost far more speed than MTP can give back. And if you mostly use Qwen for creative conversation, expect a smaller improvement. MTP works best when the next tokens are predictable. The answer is not simply turn it on. The answer is turn it on when your workload can use it and your memory can hold it. Qwen 7B really can become dramatically faster without changing the model or buying new hardware. But 3 times faster is an exceptional result, not the normal experience. For many systems, a gain of around 30% is more realistic. Coding and structured output can reach much higher because the MTP head can predict their repeated patterns more accurately. The most important rule is simple. Keep the model inside fast memory. If enabling MTP pushes anything important into system RAM, the upgrade can quickly become a slowdown. So start with draft. MTP. Use a draft depth of 2 and measure a real task. The fastest setting is not the one with the largest number. It is the one that finishes your actual work sooner. If you want more local AI tests, setup guides, and real hardware comparisons, subscribe. I will also show how to run Qwen 3.8 27B on different hardware and connect it to a local coding agent.